Okay, this is number 8 in section 5.6, and I went ahead and I just did the problem on paper. It took about 3 pages. I figured just explaining it instead of explaining it and writing it at the same time, it might shorten the video since they've been pretty long. Okay, so this is number 8, and the main difference in this section is we have repeated roots or repeated eigenvalues or multiple eigenvalues, and that's really the only difference. And we talk about multiplicity because that's usually when your factors, when you have more than one factor that's repeated. So let me just go ahead and make this a little bit bigger. So this is the given coefficient matrix that we have. So our usual, right, our characteristic equation that we're going to use, where our identity matrix, right, is that's a 1, 1, 1. Hopefully the green, that using a green pen doesn't, I hope it's fine. So again, we've been done this many times. I went ahead and I took the determinant, right, of this guy, and notice that I added the 2 columns, right, this guy and this guy, because I want to find my determinant using these kind of product of arrays. And basically, right, I started here and I went down, right, so I have this guy, this times this is this guy right here, and then I have, right, 12 times 0 times 6, right, that guy is this guy right here, right, and then my 0 times negative 18 times 6 is right there, and then we subtract the bottom, going from bottom to top. And we have, right, so 6, right, we have negative 5 minus lambda times 0. So we have this times this times this, right, and this times this. But notice that there's a 0 here. So, I mean, anything times 0 is 0. So I went ahead and I just put the 0 there. So again, I'm multiplying, right, this guy, and this guy out. Connect that, and that's my 0 right there. And similarly, right, 6 times 0 times this factor, but again, that's just going to be 0. And finally, I have 13 minus lambda times negative 18 times 12, which obviously doesn't give us 0, so I made sure to write that in. So again, this is just algebra. And I went ahead and, okay, so I have this guy, right, my factors, my 3 factors. Again, all this is 0, all this is 0, right? I basically eliminated my zeros because anything, if I add or subtract 0, I don't get anything. 12 times 18 is our 216 here. And let's see, let's make sure I didn't miss anything. So minus, okay, so here, so this is 0. Okay, so this is gone, this is gone. There's my 13 minus lambda, but I still have that negative in there, so I'm, have to multiply it in. So that's why this guy is positive 216. And here, this is where it can get very, very ugly. So what you want to do is, instead of multiplying all of this out, right, FOIL this out, double distribute, however you want to call it, multiply these factors and multiply this one and then distribute, and then, combine all your like terms and you get your polynomial. But you don't want to do that because you want to factor, because you want to find the roots. So you want to do the opposite of multiplying, which is factoring or unfoiling. So what I want you to see is, let me just get a different color here. So notice that there is a greatest common factor there, right? My GCF is 13 minus lambda. So I'm going to factor, this guy out. So this is my GCF here. And, well, what's left over? Well, we're just dividing out. These 2 guys are left, so that's why I have that there. And then my 216 is left. Again, so I factored this guy out. Now here I do want to multiply this out because I'm adding a term here. So I'm going to factor again. But here I want to multiply this out, and I get this guy after adding 216. And then I know 13 times 7 is 91, and then if I add those guys, I give you I get negative 20. So here are my three factors, and notice that 13 minus lambda and lambda minus 13, right? They're basically, the only difference is a factor of a negative 1. So I basically wrote, let me get a different color here. I wrote, so where's my, let's do this. So maybe green's not the best color since I used green. Okay, maybe this light blue, maybe make this a little bit bigger. So I have this 13 minus lambda, and maybe make this a little bit thicker. So there's my 13 minus lambda. That's the same thing as lambda minus 13 times negative 1. If you multiply it out, it's the same factor. So, I mean, you notice we have, right, three factors here. That negative 1 is not going to really matter because if you multiply both sides by negative 1, it's, I mean, 0 times negative 1 is 0. And so here's your two factors, right? Your repeated root or your multiple root. We have two factors of lambda minus 13, so we can just write it more succinctly as lambda minus 13 squared times our lambda minus 7. And I just went ahead and wrote my two eigenvalues, right? Those are the unique ones. And the book, I believe, calls this K, and your multiplicity here is 2, right? If there was 3, your multiplicity would be 3, and so forth. And we call this the defective eigenvalue, right? The one that is repeated. So I will go ahead and stop here, and I will continue in the next video. I actually do have the PDF here, if you actually would like to see. I'm going to flip. Okay, let's continue number 8 on 5.6. So this is page 2. So in the last video, we found that the eigenvalues were lambda 1 was 7 and lambda 2 was 13, where 13 was our defective eigenvalue. So that's our repeated root because our multiplicity was 2. And so now we want to find the associated eigenvectors. And remember that, okay, so we have lambda 1 as 7, so we want to find the associated eigenvector for that guy. And our defective root, which is 13, is associated with a V2. Now, there's two, again, 13s, but we know that they're not unique. They're the same thing, but by definition, each eigenvalue has an associated eigenvector. So I'm going to go ahead and have to find, I don't want to call this V2 because it's not going to be the same thing. I don't know, you can call it V2 bar if you want. So this is kind of what we're doing this part. We want to find our associated eigenvectors. So here I went ahead and I inserted my, let me get a different color here. So let me just write this. Okay, so 7, 7, 7, right, into my A minus lambda I matrix, where lambda is 7. And after simplifying that guy, this is what I obtain. And here, you can work with this matrix. I went ahead and I just simplified it because we can. Here I have 6, 6, 6. I can divide that or multiply it by a 6th, then I just get 1, 1, 1 because 1s are nicer than 6s. I did some row operations here. I added these guys, right, and I get zeros. Here, right, I just notice I put divide by 6 or multiply by 6th to this row, and then I got this matrix here. So again, if you want to work with this matrix, that's fine. You have your calculator, but I mean, zeros, 1, 2, and 3s are nice to work with. Okay, so then I went ahead and I went to my calculator, right? This is a 3 by 4, and I'm going to use my RREF function. I call this matrix A, and once I punched that guy in, my row reduced echelon form of this matrix is this guy here. Now notice we get this row of zeros, right? So we get a 0 equals 0, which is obviously is a true statement. But we want to find relationships from these rows because we're interested in knowing what x, y, and z are. Okay, so let's translate these coefficients into actually into actual equations. So we have, right, x minus 2z. Here's my x, right? There's no there's 0 y's minus 2z's, so that's how I derive this equation. And then I have y plus 3z, which is this equation. And notice I can express x and y, right, in terms of z. And if z is just called a free variable. I'm not sure if they talk about it in the book or not, but it's z is just called a free variable, your independent variable in this case. And so we have some relationships, so we can definitely, I mean, z is free, so we can definitely pick anything. Z can be anything. So if z is 1, then obviously x is 2. That should be a 2 right there. And then y is negative 3. So we have our first eigenvector that's associated with our eigenvalue 7. And I'll go ahead and do the next value, our defective eigenvalue, which again will have two eigenvectors that are associated with our eigenvalue, because again, it's a repeated root. There's one unique one, but we really still have to think about it as two eigenvalues. But I'll go ahead and discuss that in the next video on page 3. Here's the last part, and then we finally get our general solution. But I'm going to go ahead and explain this, but I wanted to give you a, since it's on video, you can probably pause it. But I'm going